Now that we have our equation, our estimated regression equation, we need to determine how well does it fit the data. So we can do that with a metric called R squared, the coefficient of determination. So this coefficient, again, it tells us how well the estimated regression equation fits the data. It ranges from 0 to 1, where 0 means it's a poor fit, all the way up to 1 means it's a perfect fit. So basically, the higher the value, the better the fit. So let's break this down and kind of think about what it means. So if we can kind of think about our original equation, our original regression model in terms of y, our outcome, being contingent upon basically some type of predictor variable and its intercept, right, that part, and then plus some type of error, epsilon, right? So if we think about this in terms of sum of squares, we can think about total, right, the total, because y is equal to all of these things. So the total, right, is equal to our regression part, right, our regression equation right here, plus some type of error. So if we think about this, we kind of have the total sum of squares is equal to the regression plus error. So everything we want to know really is the sum of regression, right, our true model of what we think predicts this outcome, plus some type of error. So the idea behind this is that if we want to know how well our data are fitting this estimated regression equation, well, if we divide our regression sum of squares by our total, right, this will give us the proportion of our total y that this regression sum of squares contributes to it, right? The larger this value is, the better our y is being predicted by the regression part, which is basically x. So if we think about our pizza example, if we're trying to explain total sales, right, the total, our outcome, everything about sales, and we're using student population size, right, as part of the regression as x, right, if that's doing a really good job explaining it, then this proportion should be pretty large, meaning that regression should be taking up most of the total sum of squares. So this value will end up being larger. So the higher this coefficient, the result of this, the better the equation fits the data. So again, if you're visual, different way of looking at this is that if we're trying to explain the total sum of squares, and it is equal to two parts, the regression and error, right? The more of the regression that's explaining the total sum of squares, the better. Because remember, our regression really is our predictor variable. So the more our predictor, right, student population size, is contributing to explaining our outcome, then our model probably should do a good job of fitting the data. So the larger the regression sum of squares is, right, it's going to explain more of the total variation in the total sum of squares, or the outcome y, so it's going to do a better job fitting. So that's just a way of kind of thinking about this conceptually. So if that's how this works, right, we need to kind of figure out how to calculate all of these sum of squares. So this is the relationship between them. The sum of squares total, right, equals the regression plus the error, and then this coefficient of determination, right, R squared, is defined by the sum of squares R, regression, right, divided by the sum of squares total, which is what we're kind of trying to explain here. So this is the equation that we want to solve for in order to determine the coefficient of determination, which will tell us how well our data fit this estimated regression equation. So let's try this one more time in terms of thinking about the equations and what they mean. So the first one is the sum of squares error, right? We've already talked about this. So when we have our estimated equation, right, that's this green line, and then the dots represent observations. So the difference, right, between the dots and our predicted line, right, we already talked about that. That's a deviation, that's a residual, that's error. So if we take all of those differences, we square them and we sum them, that is going to give us the sum of squares due to error, the sum of squares error. So again, if we look at this equation, we have y, which is our observation. If we find the difference between that and y hat, the predicted value, right, that's the residual. If we square that and we do that for all of these and we sum them together, that's the sum of squares error. So we have that. So then the other part we can think about is total. So total, right, if we think about this as just the mean, this yellow, or excuse me, this blue line, that's just the mean of y, right? So if we find the difference between our observation and that line, that's going to give us the total sum of squares, right? So our observation, right, the difference between that and the mean of y, square that and sum that together, that's going to give us the total deviation. So, right, so if we subtract the residual from the total, right, what do we get? We get the regression part. And the regression part is just the difference between, right, the regression equation, right, this predicted value, and the mean. So, right, so the sum of squares due to regression is the difference in our predicted y, which is our regression line, and the mean of y. So that's going to give us the sum of squares due to the regression. So now we're able to calculate all these values. So now if we have this, we can divide the sum of squared residuals by the total to get that coefficient to determine how well our data fit the estimated regression equation. Again, we use the sum of squares because the values would cancel out otherwise, because some observations are above and below the mean, and the lines another way of thinking about this is if the observations were all on the line, all of these dots were on our green line, the sum of squared errors, right, would be 0, because the difference right here would be 0, because, right, all of our observations would be the predicted values. They'd always be on the line. So the sum of squared residual, the regression, sorry, I always think residual, would equal the sum of squared total. Why? Because remember, our equation was sum of squared total equals a regression plus error. So if regression, if error equals 0, then the sum of squared total equals the sum of squared regression. So then if we were to calculate our coefficient, right, we would just be dividing the sum of squared regression divided by the sum of squared total by itself. Anything divided by itself is 1. So this totally makes sense because our coefficient of determination, our R squared, would be 1. And what does 1 mean? It means it's a perfect fit, the regression equation, to the data. So that makes sense because if there's no error, then all of the points are exactly on the line. That means there's no error. That means that our line perfectly fits all the data. So again, that's just another way conceptually about thinking, does this make sense? So let's go ahead and let's solve for this using our pizza parlor example. So the first thing we're going to do is calculate the sum of squared errors. So remember, let's go back to our slide. The sum of squares error is the difference between our predicted values from our observed values. So the first thing we have to do is calculate the predicted y. So that's going to, we need the equation, right? So we have beta 0 as our intercept, and beta 1, remember, was our slope, which was 5. So we can calculate the predicted value of y, right, is equal to, right, the intercept plus the slope times by x. But remember, for the slope, for both of our estimated parameters here, for the slope and the intercept, we want to keep these values the same. So I put the dollar signs in. So this is our predicted value. So we can do that for all of those. So this is basically saying that this is what we observed, but then this is what our regression equation predicted. So remember, by looking at this, our observed, and then this is what's predicted. This is the error. This is the residual. So we want to find the difference between these from our right, observed minus our predicted. So our observed minus our predicted. Right. So we're going to do that for all of those, and then we want to square those, right, because we're doing squares, right, the sum of squares. So we do that, and then remember, it's the sum of squares, so we want to take the sum of those values of those squares that we just calculated, and we get 1530. So this value right here is the sum of squares error. So let's continue on. Let's now calculate the sum of squares total. Because if we do that, right, because we have our equation right here, right, if we have the error and we have the total, we can solve for the regression, and then once we have the regression and the total, we can divide those to calculate our coefficient. So let's do that now. So for our total, right, we just want to find the difference between the observed from the mean of y. So we have to calculate the mean of y. So let's go ahead and do that. So that's equal to the average, right, of y. So we have 130 is the average, which we know, we saw that on this graph here, right, the average is 130. So the deviations are going to equal our y value observed minus the mean. And remember, the mean we're keeping the same, so what do we got to use? We got to use dollar signs. Right, so those are our deviations. And what do we want to do with those? We want to square them. So square those. And then what do we do with our deviations? Our squared deviations, sum of squares deviations, sum of, right? So we need to take the sum of those. Whoops. Right, and that is going to equal now our sum of squares total. So now what we do is we want to be able to calculate our sum of squared regression. We don't know that, but we do know that we have the sum of squared errors and the total, so we can solve for sum of squared regression. So to do that, basically what we can do is we can subtract the error from the total. So the total is 15,730, and then our error, what did we calculate that as? Is 1530 minus 1530, and we get 14,200. So that's our sum of squared regression. So, right, in order to calculate our r squared, right, what do? How do we calculate that? That's the sum of squared regression divided by the total. So we just calculated the regression, and the total is right here, right? That sum of squared here. So we get 0.9027. So this is our r squared, our coefficient of determination. Remember, let's go back to our slide. What does that mean? It tells us how well our estimated regression equation fits the data. And it ranges from 0 to 1, with 1 meaning it's a perfect fit. So we got 0.9. So that's actually really good. And if we look at our data, right, our data actually are pretty close to this green line, right? It's not as though we have dots or observations all the way up here and down here. They're all actually pretty close to the line. So again, it's good to think about the numbers that you get, the calculations, right? We know that this is a good value, so we know our regression, estimated regression equation should be doing a pretty good job in terms of being a good fit with the data. So if we look at our scatter diagram or scatter plot, right, the dots should be, right, the observations should be close to the predicted values, and they are. So this value that we calculated does make sense with what we look at. So that is the coefficient of determination and how to calculate it and what it means.